Okay, so it's my pleasure today to introduce our speaker, our PRISM seminar speaker, Vianey Leos Barajas. So Dr. Leos Barajas works on topics related to Bayesian statistics, time series, Markov switching, and spatiotemporal models. Dr. Leos Barajas' main areas of applications are in statistical ecology and environmental statistics, with a particular focus on the modeling of animal movement. So with that, I'll turn it over to you, Vianney, if you want to share your screen, and we can just go from there.
Yeah, thank you. Let's put this in full screen. Okay. Yeah, so thank you for the invitation. I know we're probably all pretty tired from all the Zoom seminars and things we can do, but I really appreciate meeting you all and being here today. Definitely feel free to interrupt me. I have now tended to favor very casual conversations about research and things. So today I'm going to talk about spatially coupled hidden Markov models, which is something that I actually started as part of my postdoc at North Carolina State University. My background is, so I have a PhD in statistics from Iowa State University. I have a theoretical math undergraduate degree, but I've always tended to find ecology and environmental folks. Like somehow I always end up like in the ecology and evolutionary biology department. I know the professors, I know the grad students, and it's just a tendency. I've always just liked these applications. So at North Carolina State University, my postdoc was actually through the Department of Forestry and Environmental Resources. And I was also sort of cross postdoc with the Department of Statistics. And now, continuing that trend, I'm an assistant professor primarily in the Department of Statistical Sciences at the University of Toronto, with a joint appointment in the School of the Environment. My collaborators at North Carolina State University were Brian Rich, Dr. Brian Rich, and Dr. Krishna Pacifici, both the most amazing people I've ever met. And I work a lot with hidden Markov models. And so this is really my path into animal movement and working with ecological data. So a simple graphical representation of a hidden Markov model, if you haven't seen it before, you basically have these two sets of random variables that you're interested in. You have your observation process Y, and you have a latent state process Z. So usually hidden Markov models, they depict this with this graphical structure. So just a basic definition, I tend to work with discrete time finite states, which means I have a K-state hidden Markov model. It's completely defined by specification of 4 components. You have the numbers of states. Your latent process Z is a Markov process. So you have a transition probability matrix that defines how you transition among those states in the Markov chain. You have state-dependent distributions, and you have initial state distributions. And what that means in practice. So why would we actually apply a hidden Markov model to something? So we usually apply it to sequential data and time series data. So the number of states means there's a sort of numbers of patterns of interest that you're interested in identifying across the time series. Your transition probability matrix then is, now that you've defined, maybe you have 3 patterns of interest that you want to identify in this time series. And then you say, well, what is the state switching dynamics across those patterns? If I'm in pattern 2, how do I switch? Is it likely that I'm going to switch then to pattern 3 or to pattern 1? How long do I stay in pattern 1? State-dependent distributions is, how do you generate data from the different patterns? So the different patterns are not just associated with one value, right? And I like to think of, so because I do animal movement, I'd like to think of like Fitbits, right? When we're active, our Fitbits can count our steps. And when we're not active, we're just sitting. So say if you're active, you're moving or you're not moving. There's a certain signal that the Fitbit can capture when you're active. And that's these are the different signals that we can generate with the state-dependent distributions that the Fitbit tries to capture, okay, it's a step or not a step. And then when we're not active, we could be sitting down. Maybe not active is sitting in the chair, but I'm still kind of moving around, but I'm not walking, I'm not moving anywhere. And the initial state distribution is, what is the first pattern that was exhibited? You can also have a multivariate hidden Markov model. So the observations process can be multivariate. And this will kind of come back into play when we talk about the spatial data. So you can still assume that there's a multivariate response, but that multivariate response is still all informing a single latent process of interest, right? So it doesn't mean we have multiple data streams and we have multiple state processes. It can, but in this case, you can also assume there's just one state process of interest, there's one pattern of interest, and it generates multivariate response. So For those not familiar, it's going to generate data from a 3-state hidden Markov model to kind of show you the data structure. So let's say we have a 3-state HMM with normal state dependent distributions. We define n equal to 3. We have state dependent distributions that are normally distributed. Let's say that we have these 3 specifications. So mean 0, standard deviation 0.3, mean 2, standard deviation equal to 1, etc. We have the following transition probability matrix. And we can see here there's more persistence in state 1, and there's less persistence in state 3, because so this is the probability that given that I'm state 1 to time t minus 1, that I'll transition to state 1. And this is a 0.8, so it's a higher probability. And the initial state distribution means when we first observe the process, it could be any of the states. So HMMs, what I love about them is that they have this different name, but they're really just mixture models. They're mixture models with dependencies over time. If we look at the marginal distribution of a hidden Markov model, so we sort of remove the temporal component, we see that what we obtain is actually a mixture model of these 3 state dependent distributions. And we can see our histograms, the histogram of the simulated data set. And then what that looks like when we observe it over time is we have some yellow, we have a few yellow points together, then we transition to the green, we have persistence in the green over time, we switch to blue, etc. Right, so when we first see a yellow point, we're likely to see many yellow points in a row. And then when we switch to green, we're likely to see many green points in a row, and etc. You can also do the blue, right? So this is just like a simulation from a 3-state hidden Markov model. Because it's just normal distributions, we have these sort of higher values that are green, middle values that are blue, and lower values that are yellow. But if you notice, we can also have some overlap, and that's okay. Because the beauty of the hidden Markov model is that you have this dependence over time that is now helping you to identify sort of which observations belong to which cluster.
Can I ask, is the fact that the colors are kind of clustered because the probabilities on your diagonal were high? I'm just trying to gain intuition for why I see a bunch of yellow dots together.
Yeah, exactly. So if this, so the diagonal entries of the transition probability matrix correspond to basically the persistence in that same state. So the reason we see a lot of yellow dots in a row is because we have the 0.8. If we lowered it to 0.5, we would see some behavior like a finite mixture model where it would be more random. We would likely not see so many points in a row. Now, if you raised it to 0.99, you would see longer sequences of the gold.
Okay, thank you. That's helpful.
Yeah. Yeah, so we could play around with these. So that's just the data set, what data could look like from a hidden Markov model. So if you have any data sets that you have already, you're like, okay, this kind of looks like the data I have. You know, you could think about, well, maybe I could fit a hidden Markov model to it. So during my undergraduate, when I was finishing my theoretical math undergrad, I had like a shark obsession, and it kind of continued through the PhD, and it kind of has just continued now as an assistant professor, which means I really wanted to work with shark data. So I always saw like the Discovery Channel Shark Week, and I was like, they have this amazing data set. They have trajectories of these animals. I could see where they go. They talk about, you know, the white shark is going to migrate from California to Hawaii. I was like, that's amazing. And they're like, oh, and they go here to forage and they go here to do this. And it's like, this is incredible. But how do they know that? You can't swim with the white shark from California to Hawaii. How do you know that the animal is doing this? And then who's the mathematician behind this? Like, there's data. There has to be a mathematician, a statistician. So I just always loved these types of applications. And this is the first project I ever got to work on. So this is one particular shark, Sarika, and she is in South Africa. And these are her trajectories. So you have multiple trajectories of Sarika over different days. And the reason that ecologists like to apply hidden Markov models to animal movement data is because fundamentally they see in their data different structures that they want to capture. So if you notice, there's like these little black dots almost, where the shark is basically just staying in that same area. And then you have these other patterns that are basically the shark going up and down the coast. So you don't see the map, but there's a coast here and it's kind of just going up and down. So sometimes it goes up and down, and then sometimes it decides to stay. And so we're curious, why does a shark decide to stay in some areas? Is there a tendency to stay in the same areas over the course of different days? And it corresponds to different energetics. So it's energetically more costly for a shark to stay and kind of circle around than it is for them to just glide up and down, right? So you think, are they eating? What's happening? So in ecology, the position data, fine scale position data, and so sorry, the trajectories were collected. It's a position every 5 minutes. It's important to say as well. So the white shark position data is transformed into what they call step lengths and turning angles. Step lengths are usually just the distance traveled, so the Euclidean distance traveled between 2 points. So you assume a straight line distance, which is an approximation of their distance traveled, and the turning angles. The step lengths are continuous, and the turning angles take on values between minus pi and pi, which means now we're going to be modeling with the circular random variable. For this particular application, we fit a two-state hidden Markov model with gamma distribution for the step length and von Mises distribution for the turning angles, with so-called discrete random effects. I hadn't heard about discrete random effects until working on this application, but there's a great book by Walter Zucchini, and basically assuming that there's different transition probability matrices because of the short trajectories. So sometimes you might not be able to follow a white shark for very long between these trajectories, and the whole time they might just be exhibiting very different state switching dynamics than you would if you saw them like the entire time, or you saw them like for a week straight.
Can I ask two
Von
quick
Mises.
questions?
Mm-hmm.
So one question, I guess I'll just ask Daphne's question, which is in the chat, which is if you could just say a little bit more about what the von Mises distribution is.
Yeah.
And then my question I'll tack onto that, totally unrelated, is whether you're using any depth information about the shark, or you're really just considering this all sort of projected onto a plane.
Yeah. Okay, so von Mises distribution is right. I know, so I had no idea what circular random variables were until I worked on these projects. And if I had never worked on these projects, I would never have encountered any circular data, circular anything, because I never actually saw it in my core, in the core courses that I took at Iowa State. And we take a lot of courses at Iowa State, so I was confused as to why I'm not seeing this. But basically, a von Mises distribution is to model circular random variables. So you have the two common ones that I've seen are the von Mises and the wrapped Cauchy. And so you have to have a manner to place probability mass between minus pi and pi. And the key point is that values close to pi are also close to minus pi. Right. So I'm not an expert in it, but there has been quite a bit of work with applying hidden Markov models to circular random variables. So just the basic is the von Mises and the wrapped Cauchy distributions are essentially just to work with circular random variables. You can either define it minus pi to pi. I think I've seen others do 0 to 360, depending on you do radians or degrees. And then we did not include depth here. And the reason we didn't include depth was because they didn't have 2 pi in radians exactly. Sorry, I'm just funny with Daphne. And we didn't include depth because in this case, so all of these tracks are actually manually collected. So there's someone on the boat, so they have a tag on the white shark, and they have to then, so they have like the shark has a transmitter, and then they have to be on the boat and get close enough to the shark to pick up the signal. And so all of these tracks were actually collected for all the different sharks, collected over years. And Alison Towner, who I think is finishing her PhD now in South Africa, she just gets on these boats and she follows the white sharks. So if it's rough weather conditions or whatever, this is the data collection process for these white sharks here. There's other animals that are easier that you can just actually add a collar to it, and you can have like a GPS transmitter. But for some reason in the marine world, they use these other transmitters. Maybe because the sharks can leave, right? They might just head out. There's something else in the chat. See? is a discrete random effect that consists of a multinomial drop from a finite set of transition matrices. Yes, exactly. So I won't get too much into it today, but Walter Zucchini, he has a hidden Markov model book and he talks about discrete random effects. And Antonello Mariotti is another name in HMMs. But essentially, what then you can kind of see is if you do what's called state decoding. So state decoding, in this case, we fit a hidden Markov model as kind of the data generating mechanism. So sometimes you have like Gaussian mixture models or finite mixture models and you want to use them for clustering. And in this case, the HMO is really evaluated as a data generating process. So we can look at residuals, and we can look at other goodness of fits measures. So in another sense, it's kind of like applying it in an unsupervised way. So a byproduct of using an HMM is that you can then assign observations to different states. Since we just had 2 states, it was very easy. And this is sort of a hard-coded results, right? I'm not accounting for uncertainty here in the state decoding results, but you can essentially see one of the tracks here, the shark is traveling directly, and then at some point it's going to stick around. So the big question for this analysis was, how are the chum boats affecting the movements of the white sharks in South Africa, in particular this area, right? So everywhere you see red, that is where there is actually tourism boats and they're chumming the waters because they want to attract white sharks. And you know, that's an avenue of revenue in that area. So basically you can see like where they're sort of chumming, the sharks tended to then remain in that area. And that could be 2 things. They can either be, they're chumming the waters where the sharks are already likely to eat, or that the chum is actually affecting how they're actually moving. But it's at least nice to see formally that there is this area restricted search patterns, what they call them. So they call this sort of like traveling, and they call this area restricted search when their sharks are remaining. There's higher probabilities of being in that type of state when the sharks were around the chummed waters. And if you see a little shark fins here on the map, this is where they actually saw a predation attempt. So the white shark would actually come out of the water and try to predate on a seal. So as a PhD student in statistics, I was like, there has to be a way to work with shark data. And this is the first project that I got to work on. So statistics students, applied stats students, master students here, I mean, there's tons of fun things you can do. I've also worked with Oceanic white-tip shark data, and that's collected from accelerometers, data collected from accelerometers. And this one, they put the accelerometer on the fin of the Oceanic white-tip shark, and then they have to recover it a few days later. So accelerometer data now is being collected more and more. That's also what's in the Fitbit, but they're now collecting it for sharks. We summarize the 3-dimensional data stream for acceleration into overall dynamic body acceleration, which essentially is just the it gives us an idea of how much energy the shark is expending. So overall dynamic body acceleration can be used as sort of as a proxy for energy expenditure for animals. And the fun thing about an HMM is that it's so flexible. You can actually define the state-dependent distributions with very flexible forms. So you could do something like a semi-parametric state-dependent distribution. It doesn't just have to be from the parametric family or exponential family. And we use penalized splines. Right? So we now have a mixtures of B-splines. And we added a penalty term and did inference for HMMs using this framework applied to Oceanic white-tip shark data. And if you notice, here's the histogram, actually the log of the ODBA. And when you try to fit parametric distributions to this very fine scale data that they're now collecting, what you'll probably find is that you'll need a lot of parametric distributions to capture the sort of fine scale structure of the histogram. So one thing we've kind of been looking more into is, well, what if we biologically, there's a need to only maybe fit 3-4 states? Like biologically, these patterns that they really can interpret more than maybe 3 or 4 different signals. So you can try to fit some flexible forms. This is something that statistically is really interesting to me. But essentially wanted to capture this peak, and wanted to capture the higher peaks here on their own. And here we see the B-spline and the distributions for each state. Right, so this green is capturing this tail. And if you look at the time series on the log scale, essentially here we have these lower values, slower signals that are basically all gold, higher signals that are mostly green, and the sort of the middle is blue. And of course, there's some interplay. There's some gold in the middle, some blue above. But again, this is an idea of how much energy are the sharks expending, and when they're sort of expending the sort of middle amounts of energy, do they do that for quite a bit of time? Do they only expend high amounts of energy for short bursts? You can sort of capture that with the hidden Markov model. And these again are sort of like hard-coded results of connecting an observation to a state without presenting uncertainty. But we also overlaid it with depth because the sharks can sink easily without expending much energy. That's actually the gold here. So if you just had this, you could actually almost figure out how the shark is moving. The gold is kind of where they're sinking. The blue is kind of when they're remaining in the same depth. And then the green is when they're sort of ascending. And I guess sometimes they ascend in spirals going up, so they expend much more energy. And they think that might be more related to how they're foraging where they are. Right? And a lot of the fun of working with this type of data is that this is some of the first data that they've been able to collect from these sharks in these systems. So you might not have 50 sharks with accelerometer data for months, but you get to do a lot of sort of exploratory modeling and what are these sharks even doing? And it becomes it's very interdisciplinary work because you have to root yourself a lot in the domain expertise of the biologist to make sure that what you're doing makes sense, especially with such data limited settings. But I like to work with shark data, position data, accelerometer data. So just kind of wanted to present this part. I tend to work on extensions. I like to incorporate multiple latent states into modeling of animal movement. And it's kind of the idea that you have fine scale movements that you're interested in, and then the compositions of those fine scale movements can inform another process that you might be interested in capturing as well. And this is kind of similar to speech recognition where hidden Markov models have been used as well. I've also been working on blending time series at different temporal scales with hidden Markov models, right? So if you have accelerometer signals and the accelerometers they have 20 observations per second. And like you said, Robbie, before, what if you also have depth? And so for marine mammals, they're actually doing this quite a bit more. They have accelerometer data and they have depth data. I know of one project on killer whales at University of British Columbia. I have another friend at Calvin University in Michigan who's doing this to understand the effects of sonar on marine mammals, particularly beaked whales. And so you have these sort of same behaviors of interest at these larger temporal scales, but you have fine scale data in between. So the idea is, depending on the scientific question, rather than summarizing all the data streams at the same temporal scale, so maybe averaging over the fine scale process, you have one observation per every 2 minutes when they collect depth data, is that you model the fine scale process as well. And maybe that provides some biological insight into what they might be doing, right? So, but today we're here mostly so I can chat a little bit about weather data, which is also something that's quite new to me. But I can include where are we going? Oh, I went far. Sorry, it's trying to open the chat up. You mean have HMMs inside of HMMs? Yeah, exactly. So Mark Scott asked in the chat about having HMMs. So I've multi-scale HMMs are just mixtures of HMMs in that context. And in the chat, what I've added is the link to where you can find this weather data that I'll talk about in a bit. So it's open source, and if you're interested in this, you can certainly get the data on your own and play around as well. So the data set that we're working with is from the Bonneville Power Administration. And there's different meteorological stations across Oregon. I think it gets into Washington a bit. So you have different topography as well. There's the sort of mountain range, there's the Cascades. There's different meteorological stations. And the great part is they have a lot of data open. I think it's every 10 minutes that they'll have a measure of wind speed and other characteristics. So I can show you quickly, there's So for example, wind speed at Tillamook Meteorological Station. These are about 1,000 data points. So you can just kind of see the speed. And Markov switching models, hidden Markov models, and what people will call Markov switching models, I tend to kind of group in the same modeling framework. But these hidden Markov models, specifically referred to as sort of Markov switching models, are common in modeling wind speed. And if you think that perhaps there's different dynamics in the wind speed, so you had to pick a model, there's periods where they're sort of elevated winds. There's periods that are more volatile. There's periods where you don't have as much variability in what's occurring. So hidden Markov models and Markov switching models for this type of time series data can be sort of a way to approximate a non-stationary process, or something that's has maybe much more dynamics that maybe we can incorporate into a single model. Although you can also try to think that maybe there's these elevated periods and you want to just distinguish between periods of higher wind speed and periods of lower wind speed. One of the primary interests for modeling wind time series data is to do forecasting. And I am definitely new. Frequency of the x-axis is 10 minutes. Our data average during that period are one-time measurements from the chat. I believe, I can't remember exactly if it's average over 10 minutes or if it's a snapshot at 10 minutes. I have to get back to you on that one. But yeah, so Brian Rich at NC State tends to work a lot with environmental data. So we were looking at this data saying, like, well, we always want to do forecasting. And in part, the reason to do forecasting for wind speeds is that you can not only think about the wind dynamics of how well can we forecast, 6 hours, 24 hours, but if you're also thinking about wind production, wind energy, there are, if you have, you might want to think if the next 24 hours, how might the wind look like over the next 24-hour period? Is it going to be a good day for wind energy production? If the wind is too high, they'll have to turn off the wind turbines because something might happen to the wind turbines. If it's too low, well, is it worth it even then to turn on the wind turbines and lose that energy? So Markov switching models in particular have been good for short-term forecasting. And in general, what this took me down the path of is spatial data and hidden Markov models. How are they used? So two common approaches to fitting Markov switching models / HMMs to spatial data that I think is more common is that you assume that there are k spatial processes that generate the data. So like before we had our multivariate HMM, you can have a multivariate response in the single state process that you're interested in. And that single state perhaps then generates a spatial process. So that multivariate data has maybe a covariant structure and you can incorporate some spatial dependence. Or you can assume that each location is maybe independent of each other and you fit an HMM to each particular time series. So Brian and I were thinking, well, what if we wanted to allow for multiple state processes to occur across a spatial domain, but that locations close to one another should behave similarly in their state process? Just a quick visual. So if you have these sort of purple and green states over time, you might have a 3x3 grid where you have green circles here and purple circles here. At the next time point, then what's likely to occur? Are the green likely to switch to green? Are the green likely to switch to purple? And so the idea is that these two green here have a few, well, this green definitely has a few purple neighbors. So maybe it's likely to become purple the next time point. And again, the next time point, where there's a lot of green, it's likely to remain in the green. And where there's a lot of purple, it's likely to remain in the purple. But depending on the neighborhood structure, it might switch between green and purple. So this is kind of what we wanted to do. We don't want to assume that there's just one state process, which would be it's all purple or all green at each time point. And we don't really want to assume that they're just independent of each other. We say, well, what can we do that's sort of in between? So statistically, this is where I've been having a bit of fun. And I'm working on applying what is called coupled hidden Markov models to spatial data. Coupled hidden Markov models, the idea is that the quantity of interest here, we can look at this diagram, sorry. So suppose you have two observation processes. So you have two latent state processes as well. And there's going to be some interaction between them, right? So at time 2, this state process depends on the state process state at time t minus 1, which would be state at time 1. But it also depends on what occurred at time 1 for this other state process as well. So you can incorporate it almost as covariates, which means that in your HMM framework, the quantity of central interest for a coupled hidden Markov model is then in your transition probability matrix, the probability that ZT, the state at location n at time t, depends on all of the other state processes at time t minus 1. It's almost covariates, more like latent covariates. Yeah, latent covariates. Sure. Right, it's an unobserved process. So I was primarily interested in how have the coupled hidden Markov models been used in the statistical literature. I think it's more prevalent in the machine learning literature and activity recognition literature. So Brad et al., 1996, he has a few papers on coupled hidden Markov models. There's activity recognition when multiple movements across the body influence one another. And I like to use the example that is when I'm talking, I'm usually moving my hands in some way. And if I'm moving my right hand, it's likely that I'm going to move my left hand in some way. Or if I'm walking, my right leg is going to now, my left leg is likely to move as well. So if I'm moving my legs, they have this sort of interaction with one another. But the primary way I've seen it applied in statistics is through progression of diseases. So modeling of disease progression, when there are maybe multiple diseases that could be interacting with another, and they might influence one another. There's a great paper, Sherlock et al. 2013, coupled hidden Markov models. And there's another paper that I'll bring up, but it hasn't really been commonly used. Right. So the idea behind the spatially coupled hidden Markov models is that you again have multiple latent state processes, but really, instead of like our quantity of central interest here, we're at location n time t, this state depends on all other state processes at time t minus 1. Now there's only interactions with some of the states. So this location n time t minus 1 will only affect and will only affect a few of these state processes, but not all, right? So we don't have the arrows pointing to every other state process, which means that the quantity of central interest for a spatially coupled hidden Markov model is close to what a coupled hidden Markov model is, except now we only care in incorporating, as Mark said, the latent covariates that are neighbors of that location. So ZT location n depends on ZT minus 1 at location n. And this part here is just like a basic hidden Markov model. But now we incorporate the state processes that are neighbors of that location. So the state process location n time t depends on t minus 1, as well as its neighbors. And there is certainly an assumption that we've made of how we might incorporate the spatial dependence and the spatial parameter in this coupled hidden Markov model framework. If you all in the chat right now told me I don't agree with you, I think you could do it better this way, I don't think that's correct, I would also agree with you. I think this is something that's really new. Coupled hidden Markov models haven't really been adapted to spatial data, at least not that I've seen in the statistical literature. And so we are making some assumptions of maybe how can we simplify this, make it as simple as possible, include a spatial dependence parameter into for the functions of the transition probability matrix entries. So what we're doing is essentially incorporating this indicator function to count the number of states that are neighbors to that location of interest, that are equal to the state that we're transitioning into. So gamma sub ij, this is the probability that given that you are in state I, which is really a vector, now we incorporate multiple state processes that you transition to state j. That might have been a bit confusing. But the idea is that you just want to incorporate the sort of spatial dependence. And how you can do that is really open right now. So for the simulation study, what we're first working on right now is we're just assuming a Rook neighborhood. And we're constructing this very nice 5x5 grid. And we have the Rook neighborhood structure. So for example, in a basic hidden Markov model, if you have no covariates, you have a time homogeneous process, which means your transition probability matrix entries are not going to change over time. In this case, since you're incorporating the sort of latent covariates, you now have a time inhomogeneous process because you're incorporating what's occurring at the other state processes into your transition probability matrix. So for instance, if you have a 5x5 grid of spatial locations, say location 1, 1, we'll now have neighbors 1, 2, and 2, 1, if we incorporate this Rook neighborhood structure. And if we look at just one entry of the transition probability matrix, so gamma 1, 1, which means what's the probability that you were in state 1 and you transition to state 1? How do you define the neighborhood structure? Oh, yeah. You'll see that here, it doesn't vary very much over time because it likely really only has 2 neighbors. It's not as influenced. But so the probability transition of from state 1 to state 1 over time remains pretty constant. But if you look at any other position where it has more neighbors, now, so this location has 4 neighbors here, there's a lot more variability in the probability of transitioning from state 1 to state 1 for that location. It's going to be much more variable. So again, this is something quite new that I'm working on. We started working on it together at NC State, and I'm still working on it now. But this is sort of just it's kind of a fun manner as well to think about just Markov switching processes for spatial data and how we're really defining the state process over time. So for the state dependent distributions, in basic coupled hidden Markov models, what you do is you assume conditionally independent observations given the state process. What we're doing is assuming autoregressive structures. And this is simply what's more common in Markov switching processes for wind time series data. So you can assume a basic AR1 structure. So it's conditionally independent observations given the states and the observation at time t-1. And we're applying this framework to data collected from the meteorological stations. So the link that I've included in the chat from the Bonneville Power Administration. So again, we're interested in short-term forecasting. In particular, Brian has a bit more experience with this. But in the literature, Markov switching models are flexible and they perform well for short-term forecasting of wind speeds and directions. Now, I've had this conversation with Adrian Raftery earlier this year when I was at UW. And he asked me, well, you have these Markov switching models. I don't think they're going to do well in long term. And I agree. I think they're really flexible, so they can capture a lot of great dynamics. But maybe for longer forecasts, you actually need sort of physical processes and really understanding of the climate and the wind dynamics across that area. But for short-term forecasting, Markov switching models actually do quite well. So it's kind of maybe a cost benefit of what you actually want to do, but in this case, they have been quite useful. So the idea is then, can we adapt the spatially coupled hidden Markov model then to create forecasts? And again, it's sort of as the statistical side of what really interests me is how you conduct inference. For HMMs, and now I have a few HMM papers, I've actually never used the EM algorithm, expectation maximization, and I've never used anything like Gibbs in Metropolis. In particular, because my preference for fitting hidden Markov models is to marginalize over the latent state process. Work directly with the joint distribution of Y only, which is you can refer to as a marginal likelihood. And I use Stan basically for everything that I do in practice. Hamilton and Monte Carlo, specifically, I've always loved. But it's not feasible for coupled-tandem Markov models. And I think this is perhaps why it's not as commonly used in statistics, is that they might be a bit hard to fit. So the idea here, since I can't really marginalize over the state process, because even with just 25 locations, the likelihood evaluation can be computationally demanding. So I'll do a sort of Gibbs metropolis. You can also use Hamilton and Monte Carlo. So the idea is you'll alternate between updating the states and updating the parameters. I use the forward filtering backward sampling for this. So you generate state sequences. So you generate one draw from the joint posterior distribution of the state process using the forward filtering backward sampling algorithm, and then update the parameters. In this case, I'm using a combination of conditional conjugacy and Metropolis Hastings. There's a great paper, Scalable Bayesian Inference for Coupled-tandem Markov Models, that just came out last year. It could have been earlier this year as well. My timeline is a bit off. That talks about actually how to do inference for coupled-tandem Markov models. And hopefully this will also be a reason that we start using coupled-tandem Markov models a bit more in statistics. And the computational challenges. So I love fitting hidden Markov models, but I'm really, really good at failing to fit hidden Markov models to data. And in part, exploration of the parameter space, when you have a discrete state space, you have multimodal posteriors. And in large part is when you have when you're trying to fit a hidden Markov model, I usually fix the number of states that I'm interested in, and then I fit the hidden Markov model. So I'll say, well, I'm going to fit a 2-state hidden Markov model to my data. And what happens is that you have multimodal posteriors, and just doing basic simulations, you can start to understand, well, why do I get multimodal posteriors? And it's usually some type of model in the specification, or they're so flexible that you sort of need to regularize them in some way. This is why I like to do Bayesian inference, because I use my prior not only as a way to incorporate my domain expertise, but also as a way to regularize, to try to sort of lessen what people call spurious modes in my likelihood function that then manifest themselves in the posterior. So you do have multimodal posteriors. And in this case, you also now need to select the number of states at each location. So you can make the assumption that in 5x5 grid, 25 locations, each location will have 3 states, right? But that's certainly an assumption that you'll need to make. And then the problem is that if it's really misspecified at one location, it's going to manifest itself as a multimodal posterior and affect inference from my other dynamics that I'm interested in. So computationally, I think this is a bit interesting. Even for basic hidden Markov models, I tend to go into a lot of detail of why are they multimodal? What is going on? Why are they not well identified? Oh, sorry, I see a chat. How do you have different states, different numbers of states at different sites? You could do that. I thought the point was to share states across sites. I will happily, we can have that conversation after. You could do that, right? So that could be the point of doing this, or you could, yeah, I'll save that one for later. So, and in particular, when I'm incorporating or deciding to create, we adapt like coupled-tandem Markov models to spatial data. I'm also curious of, well, how do you build to a spatially coupled hidden Markov model, right? How do you actually do the model building to that? So something that I also like to work on is simply like model building strategies. So anytime you have a new HMM structure that you're applying to data, or maybe it's not new, but it's new to that area, how do you actually build up the spatially coupled dynamics? Like I said, there's other computational problems that'll likely occur. The number of states, which I think was kind of what Mark is saying, is to share states across sites. I think there's a tendency to try to identify, well, what is the true number of states for my time series, for my data? But what I've seen also, it can depend. If you have more data, you might end up needing more states. So I'm sort of trying to transition from the true number of states for a certain process to the number of states that can be resolved by the available information, by the model specification. And in general here, what we'll have to do is do a more Monte Carlo forecasting procedure. For a basic hidden Markov model, the forecasting distribution can be obtained, can be obtained in closed form. And Walter Zucchini in his HMM book does a great job of explaining how. In this case, we're going to do Monte Carlo simulation for forecasting distributions. So this is, I wish I had gotten a bit further on this work. We have basic simulations up and running. We have the MCMC code running. But I hope we at least understood just the spatially coupled motivation, some HMM and Shark examples. So we're finishing up actually analyzing the data. I'd like to write the MCMC code a bit more efficiently, but it's actually not too terrible. And like I said, this is sort of the first time that I've seen in the statistical literature that we're applying coupled hidden Markov models to spatial data, which means that the way that Brian and I are working on this together, it could possibly be only one way. And like I said, if you'd like to disagree, there's probably lots of different things you can do, and it depends on what we're actually trying, the scientific question at hand. And so what we're trying to do is just provide like a foundation of here's one way of doing this. And then if it provides motivation for people to do it better, for people to do it in a different way, I think that's great. So thank you for having me. Thank you for all the questions as well. It's been great. And yeah, thank you for coming.
So thanks so much, Vianey. We can sort of all clap using our reactions, or give you a hand like this. So yeah, let's open it up for questions. And as usual, I'd like to particularly encourage any students to chime in and ask questions. So go for it. Leo, looks like.
Yes, thank you, Vianey, for your presentation. I was just wondering, for your wind data, what distributions are you including in your likelihood? Are you modeling the speed and the angle together, or?
Yeah, so a lot of papers, right, totally correct. They model speed and direction. In this case, since this project is a bit more on the methodology side of seeing, how can we actually fit these spatially coupled hidden Markov models. We've just been developing it for wind speed, but we could also incorporate direction. In this case, using these circular value distributions would be interesting to add as well.
And do you have normal data, or do you assume gamma distributions or something, or just a sort of
Yeah.
mixture of?
So for now, we're doing each state-dependent distribution is an autoregressive process. So it's an AR1, and you could obviously also extend it to do an ARP or a vector not a vector autoregressive, we're keeping it for right now as a univariate distribution.
But what's the underlying distribution for your ARP?
So we have the normal, the error term is normal.
Okay. And will you truncate it somehow, or?
We likely should try to truncate it at some point, right? Because the dynamics, the wind speeds probably can't reach a certain level. So you can probably incorporate some mechanism where it's like, you get to this point, you're likely going to now be decreasing in wind speeds. So yeah, that's something we should do. We'll just kind of see how it goes for now.
Okay, thanks.
I guess I'll ask a question then. So I was curious, operators of wind turbines, they surely have to be doing some kind of optimization, right? Of like when they turn their turbines on and off. And so are they using anything sort of like statistically sophisticated or anything like hidden Markov models to your knowledge, or like how are sort of these things being optimized in practice right now? You know?
That's a great question. So what I think I'm becoming a bit more familiar just with the statistical literature, and not unlike the shark data where I actually know the biologist and have gone out to do research visits with them. I haven't gone out to a wind turbine yet, but I know that in some cases in the literature they talk about using Markov switching models, and typically they'll refer to Markov switching models when you're using an autoregressive process in your state dependent distributions. And then it's a hidden Markov model when it's just like a parametric distribution without the dependence. Going to see sharks is better than going to see wind turbines, definitely. So yeah, I'm not quite sure, but I know that in some cases you do need to know when the wind might be too high, because you don't want anything on your wind turbines to break. And I know there's like some minimal level as well. So I'm not quite sure, but I know that they're interested in these forecasts, and even short-term forecasting can be quite valuable. And I think about it a bit more as taking me back into animal movement, because you need to think about it as also like eagles and other large birds and their interaction with wind turbines. So I think I'm working on this in part to try to find myself back into the animal movement world. And I can answer Mark's question as well. But the point was to share states across sites. So
can I clarify?
Yeah.
Maybe I was confused. You were doing some kind of model selection. Sorry for the video stuff. The model selection you were doing was, it sounded like you were trying to choose at any given site how many different states would be available, but initially it sounded like you had a finite 3 states, let's say, and you're deciding how much each site influences the probability of moving to each of those 3 states. So it seemed like they were 2 different things. Like one was much more flexible than you'd ever be able to identify. The second one just seemed really, really flexible. Like, oh, there could be 2 states here, there could be 5 states here. And then how do you even know which states correspond? If you have 2 states at one site and 5 states at another site, then what corresponds to what? They're almost like their own individual states. And that doesn't seem to be using any of the information over and over again.
Yeah, totally agree. What I think about is in practice. So say we assume that there's 3 states across all locations.
Yeah. And
maybe for some reason we say, well, but maybe the means vary, but there's still this sort of ordering that we specify in the states.
So you're making it more flexible. It's site dependent parameterization of the. Okay.
So you could, right? So you could do that, definitely. And I completely agree that it could be too flexible. I think about in practice. So I work with a lot of real data, and if I try to say, well, maybe I won't do site specific distributions, and I'll say there's 3 distributions. How misspecified is that going to be at the different locations if I say there's 3 across all? Like, is it actually going to work in practice? Or maybe the coupled HMM framework will only work if I have those, if that framework fits. I can do the same 3. And so that's just, it's something that since we're just getting started with this, it's kind of in practice, what is actually going to happen? And if it's maybe the 3 state assumption is going to be too misspecified at one location, and then I get my multimodal posteriors.
Right. I guess what I was worried about is sort of the classic problem of just if you're trying to borrow any strength, then you have to have some notion of homogeneity, and if you don't, then I don't know that there's an in between. Like, imagine that in one site there's a type A state, and that type A also exists in this other site.
Yeah.
But how do you even imagine being able to track that? It's like it's like you're trying to you're creating a space of possible sites and states that needs a correspondence as well. It just sounds like you're asking for trouble.
Probably. Yeah. I mean, definitely is.
Okay.
I mean, I agree. Okay. So it's so I think in part is I like to fail to fit HMMs and simulations quite a bit. So I think one thing could be just simulating this in a very small structure, and then just seeing how is it going to fail, and what patterns am I going to look like? What am I going to look for in practice to say this is not working? This assumption won't work in practice. So we can start off by assuming that there's the same sort of state dynamics, and then just the states are switching, right? So then there's just the evolution of the state sequence is possibly different across the sites. And then the next step is, can we actually extend this, or is it just going to all go out the window, as you said? And I'm not sure. I agree that it could fail spectacularly. And I agree that we do need some type of, there does need to be some notion of this is the same state as that state over here. If you assume too much that's just all different from each other, then how do you link them? And that's
yeah, that if you decided ahead of time that there's going to be a common state between these two, that works. But if you want the system to learn that this state and this state are the same, that's another parameter. It's literally the parameter of all assignments.
Yeah.
And walking through the space of parameters of all assignments is dangerous, I think, and probably really hard to program, you know, to get Stan to do that for you or something like that.
Yeah, I don't even fit the coupled hidden Markov models in Stan. And I like Stan because I feel like it's exploring my parameter space more efficiently than I would on my own, and it tells me all the things I'm doing wrong. So yeah, I'm not sure. I will.
No, it's sort of like hard clustering somehow in the middle of in a model.
Yeah.
And that's not done very well.
Yeah, no, there does. I think in this case, the way to possibly say that, you know, these are the same states, these are the different states, but they're linked, is by topography. So
that makes sense. Yeah.
If the wind stations are on the Cascades, then you could say, okay, these are going to share states, these are going to share states, and that's one way to do it here.
That seems to have legs.
Yeah.
So in the interest of time, maybe we should start wrapping up, and I'll just, I noticed Yoav raised his hand, so I'll just let him sort of ask the final question or make the final comment, and then we can wrap things up.
Thanks, and thanks for the talk, Vianey. I just wanted to say as a comment for in case anyone is in the virtual room who is interested in this methodology applied to social phenomena, that there are ways, I mean, I did some years ago, to apply hidden Markov models to student data in learning management systems where the observable outputs are like, you know, clickstream data from students who sort of navigate through learning management systems, solve problems, watch videos, pause the videos. And what's interesting, what was a potential direction for future research, which was getting sort of in deep methodological waters for me, and I kind of backed away from it, was nested hidden Markov models for that, because it is a switching process. If you think about what students are doing, sometimes they're learning, sometimes they're assessing themselves, you know, sometimes they're doing a quiz or homework or problem solving. Other times they're watching videos and reading. And so the expectation that you would have a different transition matrix for like reviewing, learning, and problem solving is very rational. So there's the nice thing about that, I don't love learning management system data, but it's plentiful. And when you want to fit hidden Markov models, you can't get like, you know, 20 time series of like 2 people doing something for 30 moves, right? You need a lot of data so you can get it. So if there's people who are listening who are sort of like, I want to do something like this, I'd be interested in talking about it, because it's something that I did once and I miss a little bit. So thanks for giving me some space to just shout that out.
Yeah, I mean, I just talked to the astrostatistics group here at University of Toronto, and they also have time series. You know, we can apply hidden Markov models to, you know, to the different like things that are occurring. I don't know anything about astrostatistics, but they have amazing time series data as well. So I mean, I think I just love hidden Markov models. They're so flexible. You can apply them to so many different domains. And then you can incorporate, you know, autoregressive structures, spatial structures, semi-parametric. It's kind of a fun way to just put the, you know, create different structures, different patterns, and have them switch between each other. You're like, oh, now it's a hidden Markov model, and I get to play around with that too. Yeah.
All right, so it's time for us to wrap this up. So I'll just say thanks so much again for the great talk, and thanks for everybody for attending.